Alright, so here's a summary of all the logarithmic rules we have gone over recently. Okay, so remember last class. So we went over the change of base formula. So here's the change of base formula. On the bottom here, we have the product rule, the quotient rule, and the power rule for logarithms. Okay, so each of these we went over very recently. Okay, another thing that also wanted to show you is to recall. So if we have a logarithmic function and an exponential function, so this is the same thing as log base b of x equals y, right? So in the context of what we went over last class, so if we spell bay, this is our base, this is our answer, and that's our exponent. So in the context of when we're writing this as an exponential function, this is our base, this is our exponent, and this is our answer. Okay, so now what we're going to do is we're going to try to put this into practice. Okay, so let's try to do some other examples. Okay, so let's say what we want to do is we want to solve for x. Our goal is to round to the nearest thousand. Okay, so now what we want to do, as you can see here, we have 2 raised to the x equals 9. So now these problems are not going to be as obvious as what I went over before. So remember what I went over before, you could figure out, well, if you multiply 2 a certain amount of times, how can you get this number? Well, if you try to do this, like if you were to go ahead and go into Desmos, you do 2 raised to the first power, well that's 2, second power is 4, third power is 3. Our goal is to get 9, right? But as you can see here, if we go 2 raised to the fourth power, you get 16. So we know that this exponent is between 3 and 4. We know that we don't know exactly what that number is. So, I mean, you could do trial and error. It takes a very long time. You could try, let's try 3.05. Wait, our goal was to get 9, right? So 9, okay, that didn't work. Let's see. Let's try 3.1, 3.12, 4, 5, 6. Oh, 3.17? That might be it. It might be 3.17. But as you can see here, so this isn't very time efficient. Just trial and error. I want to try to figure this out by not using trial and error. Okay? So what we can do is we can go ahead and just label our parts again. So if we have an exponential function this time now, this is our base of the exponential function, this is our exponent, and this is our answer. So our goal now is, if we want to write it as a logarithm, we are trying to spell A, right? B-A-E, like I showed you guys earlier. So if our goal is to try spell B, so our base is 2. Our answer is 9. Our exponent is x. Okay? So now let's go ahead and try to solve this. So remember, we can use a change of base formula. Remember the change of base formula here. So what we can do is we can rewrite it like this and actually evaluate this. So this is log of 9 divided by log of 2 equals x. So if we go into Desmos and actually calculate this, so we have log of 9 divided by log 2. And that's about 3.1699. Look at that! Wow, we did pretty good. We did pretty good with that. But yeah, that's the more accurate answer, if you're wondering. So 3.1699, so x is approximately 3.1699. If you want to round to the nearest thousand, well, this would be 3.170. Okay? Now, there's another way that you can do this. And I purposely wanted to show you this way because it involves the other rules that I showed you. Okay? So the other way that you can do this is, if we start off with that, we have 2 raised to the x equals 9. Okay? So now what we can do is we can rewrite both sides with a common logarithm. If we write both sides with a common logarithm, we have log of 2 raised to the x equals, and in this case here we have log of 9. Okay? Now, there's a little rule here. I didn't really specifically go over it, but if you don't see a number here, you actually assume it's a base of 10. Okay, maybe in the future if I show you some problems where you can rewrite it as an exponential function, maybe I'll teach you that. But just I'll just tell you that if you don't see a number there, you assume it's 10. So what this says is we can use this formula. We can use, oh, where is it? We can use this formula here. So the power rule for logarithms, because we have a base here, we have an exponent. So what we can do is we can bring that exponent down. Okay, so we can bring this exponent down, so as you can see here. And what we have is we have x times log of 2 equals log of 9. Okay, so actually what happens is basically one way to think about it, these parentheses here, you don't have to worry too much about them, and you can literally just bring this down. Okay, so then what we can do is we can go ahead and solve for x. We solve for x, we can divide by log of 2. Okay, log of 2. Okay, so what this says is, well, this will cancel, and x is going to be approximately whatever we have here. So it's going to be 3.170. Okay, so that's the way that you can do that. Okay, letter B. Okay, so we have 5 raised to some power equals 76. Okay, so we can go ahead and do this all over again, right? So like we can go to Desmos and we try to figure out what exponent will this be if we want to get 76. So we could do trial and error if we wanted to. It's going to take a very long time, but we can. Let's see. 5 squared is 25. 5 cubed is 125. Our goal is to get 76. Okay, 76. So let's see. Let's try 2.5. Nope, that's not 76. That's not 76. That's a little bit close to 76. All right, 2.68. Nope, 2.69. 2.691. Oh, maybe 0.8. Oh, we're getting there. Oh, I like that. 7? No, 8. 8.5. No, 8.4. 8.3. 8.4. Oh, look at that. Okay, so it's probably going to be around there if we go ahead and do that. But you see how long that took? That took a long time to actually try to figure out, okay, what equals 76, right? So what we can do with this is we're going to go ahead and use, what I showed you earlier. So first what we need to do is we identify our base, our exponent, and our answer. Okay, so this is our base, this is our exponent, and this is our answer. Okay, so again, our goal is we want to spell log bay. Okay, so in this case, our base is 5, our answer is 76, and our exponent is x. Okay, so if we want to go ahead and use the change of base formula, this one right here, right? So now what we're going to do is we have log 76 divided by log 5. And let's see what that is. Let's see what that is. Log 76 divided by log 5. So log 76 divided by log 5. That's about 2.9. Hey, look, we did pretty good with that. Look at that. Yeah, so if we round to the nearest thousand, it's probably going to be like 2.691 or something, 2.691. So that would be what it's approximately equal to. But yeah, so you see with logarithms, it makes our life a little bit easier to actually calculate that exponent. We don't want to sit here all day and actually try to calculate it. Okay. So what we can do is I can show you this method here. Okay, so the method here, so we have 5 raised to the x equals 76. We can write both sides with a common logarithm. So this is log of 5 raised to the x equals log 76. Now this x will drop down. So this x drops down. This is x times log of 5 equals log 76. Divide both sides by log 5. And that's exactly what we have here. So if you do that, x is approximately 2.691. Okay, so however you want to do it, that's up to you. Okay, all right, so now let's go ahead and look at this one. So letter C. Okay, so realistically, when we do this, so same idea. So this is our base, this is our exponent, and this is our answer. Okay, so we want to spell log B, B-A-E. Our base is 9. Our answer is 2/5. Our exponent is x. Use a change of base formula. Log of 2/5 divided by log 9. Okay, so let's go ahead and do that. So log of 2/5. So log of 2/5, and we divide that by log of 9. Okay, log of 9. So in this case, this is going to be, what is that? Negative 0.417. Okay, negative 0.417. Okay, so that would be, oh, that's me being bad with my notation. So this is this down here. So this is x is approximately negative 0.417. Okay, so that would be our answer. Okay, now like I told you, I mean, like, yeah, like I showed you earlier, so 9, let's try that. 9 raised to the negative 0.417. So that's going to be about, yeah, 2/5 is basically 0.4. You know, that would take a very long time if we actually tried to go ahead and solve this. 9 raised to x equals 2/5. It wouldn't be very obvious for you guys to try a negative exponent for some of you. So, yeah, we are trying to save ourselves time. Okay, so the other way that you can do this, so let's see. I'm just running out of room. I'm just gonna erase this here. Okay, so I don't need this anymore. Okay. So the other way that you could go about doing this, right? So, or what we can do is if we have, this is going to be 9 raised to the x equals 2/5. We can rewrite both sides with a common logarithm. So log of 9 raised to x equals log of 2/5. Use the power rule, bring this down. X times log 9 equals log 2/5. And then what we can do is we can divide. Okay, log 9. So this cancels, we get x equals log 2/5 divided by log of 9. And we said that is going to be approximately negative 0.417. Okay. However you want to go about doing that. Okay, so that summarizes that part. Okay, and I'll see you in the next video. Okay, bye. Hello. All right, so now let's bump up the difficulty with some word problems. All right, so let's say we have Mr. Lowe. Okay, Mr. Lowe is studying the behavior of dolphins in the ocean. You know how much Mr. Lowe loves dolphins. Yeah, so the pod starts off with 14 dolphins, and he observes that the dolphin population doubles every month. Now, there's a function shown below that models the number of dolphins after so many months. So the variable would be t. Okay, now how many months did I misspell that? How many months will it take? Okay, I'll change that later. How many months will it take for the dolphin population to reach 4,200? Okay, so, well, what we can do is, well, we know eventually we start off, so this is in the context of an exponential function, we start off with 14 dolphins. Eventually, we need 4,200 dolphins. Okay, so 4,200 equals 14 times 2 raised to the power of t. Okay, now our goal is we want to get rid of the 14 on the outside there. So what we can do is we can divide by 14. Okay, so this cancels. If we actually go ahead and do that, so if we do 4,200 divided by 14, that's going to be 300. and this equals 2 raised to the power of t. Let me just do that just to make sure. 4200, yeah. 4200 divided. Okay, that's 300. Okay, good. All right, so easy to get my phone earlier. It's charging. Okay, now what we want to do, so one way to think about it, so we can actually rewrite it this way, like flip it around. So this is 2 raised to the t equals 300. So if you guys like the Bay method that I showed you earlier, our goal is we want to write log and then Bay, right? So in the context of this exponential function here, this is our base, this is our exponent, and this is our answer. So our goal is we want to write log Bay. Base is 2, answer is 300, exponent is t. Okay, so that's how we can express this as a logarithmic expression. Now, if I asked you to actually evaluate this, okay, so I evaluate this, we find log of 300 divided by log 2 equals t. So we can use the change of base formula. Okay, so log of 300 divided by log 2. Okay, so in the context of this problem, basically what this says here is t is going to be approximately, well, let's see, I didn't say to round actually, but if we rounded it, I guess it would be about 8.229, I guess, if we round in there's thousands, so this is approximately 8.229 and months. Okay, so that's how many months it would take for the dolphin population to reset. Starting if you had 14 dolphins, then you're going to have 4,200 dolphins after 8.229 months, assuming that that population doubles every month. That's a lot of dolphins. That's awesome. Okay, now I'll show you another way that you could go ahead and do this. Okay, so the other way that you could do this is, let's go ahead and actually what I'm going to do is I'm going to take it from this step. Okay, so I'm just going to erase here, and this should be okay. I'm going to leave this on the side. Okay, so the other way that you could do this is you could do you could rewrite both sides with a common logarithm. You have log of 2 raised to t equals log of 300. Okay, then you can use the power rule. Power rule says drop that down. Drop the exponent down. T times log of 2 equals log 300. Okay, then what we can do here is if we divide both sides by log 2, so what we do is we didn't even need this step here, and then we go straight there, and that's how we would solve for t. Okay, but in the case if the question asked you to express this particular question or as a logarithmic expression, then you'd have to show it that way. But just wanted to show you there's 2 different methods that you could go about trying to solve this. So you could do the way that I showed you earlier. So I'm just going to go ahead and show that right now. So yeah, this thing right here. Or you can do it the other way, whichever method works out for you. Okay. Okay, so let's go ahead and look at another type of example. Okay. All right, so I'm just going to go ahead and take a quick screenshot of this. Okay, so with the vaccines rolling out, let's hope that the coronavirus cases will soon start to drop. Okay, so currently this was taken as of 2 days ago. Okay, so we have about 1,145 active cases in Hawaii. So we'll say that's what we started with. That's what we have now. Okay, let's hope that the active case count decreases as modeled by the function below after so many months. Okay, so what this says, yeah, so you're multiplying it by a third. every month. Okay, so how many months will it take? So yeah, will it take to reach 2 active cases? Okay, so but I see what we can do with this. So our goal is we want 2 active cases. So this gets plugged in here. This is 2 equals 1,145 times 1/3 raised to the t. Okay, so same idea. We want to get rid of this coefficient on the outside. So we're going to divide by 1,145. So we want to divide by 1,145. So this cancels. So we do that. 2 divided by 1,145. So 2 divided by 1,145 is going to be 0.001746. Oop, excuse me. 0.00, and that is going to be 174. Actually, I don't even know if I need to keep that many decimal places. We'll say 1747 equals 1/3 raised to the power of t. Okay, so again, if it helps, like you can rewrite this other way. If you flip it around, right? So this is 1/3 raised to t equals 0.001747. I can see some of you already getting lazy. Is like, okay, this is our answer. This is our base, and that's our exponent. It spells a, but I can just spell b after. That's fine. You can do that. Yeah, I'm just showing you this way. Just some of you are having a hard time labeling the variables and stuff. Okay, so this is our base, and this is our exponent, and this is our answer. Okay, so again, our goal is we want to spell log a, right? So if we want to spell log a in this case, so what we have is our base is 1/3, right? Our answer is 0.001747, and our exponent is t. So if we use the change of base formula to solve this, this is log of 0.001747, and we divide this by log of 1/3. Okay, so if we go ahead and do that, so log of 0.00, let me go ahead and get rid of this. Log of 0.00, where was it? 1747. Okay, 1747. And we divide that by log of 1/3. Okay, so log of 1/3. Okay, so it's going to be about, if I round to the nearest thousandth, 5.7798. We'll just say 5.780. 5.780. It's going to be t. So t is approximately 5.7. What did I say? 780. And that's how many months it would take. Take a long time. Actually, well, I mean, hopefully, if we social distance, that would be a miracle if we could get it down to that. I mean, realistically, probably not to single digits, but yeah, if we could, yeah, every month divide that 1,145 by 3. Eventually, in like almost half a year, I guess we get 2 active cases. That'd be amazing if we could go back to single digits, but probably not gonna happen, really. But yeah, so that's how that one works. Okay, now the other way that you could do it, so I'll just show you. So yeah, I'll just go ahead and just show you each example here. So if I can just go ahead and yeah, actually I'll take it from this step. Yeah, no, I'll just rewrite it again, it's fine. Okay, so the other way that you can do this, so if we have 1/3 raised to t equals 0.001747, so what we can do is we can write both sides with the common logarithm. So this is log of 1/3 raised to t equals, and this is log of 0.001747. Then we can bring this t down. Bring the t down, and what we have is t times log of 1/3 equals log of 0.001747. Okay, if we divide both sides by log of 1/3, we're going to get this here. And then we don't even need this part here. So this part would be completely gone, like, yeah. So what you can do is, if you want to solve for that variable, that's how you could do it. Yeah. Or, yeah, like I showed you earlier, just do it the way that I showed you earlier with the big. Okay. So whatever your preference is, that's entirely up to you. Okay. All right. So that summarizes that part. Okay. So please let me know if you have any questions. Okay. Bye. Hello. All right. So let's go ahead and bring back just some things that we went over in quarter 3. Okay. Before you guys took the SBA. So recall there's these two formulas. So for exponential growth, what we have is, if we're adding, yeah, that's going to represent exponential growth. Whereas if we subtract, that's going to represent exponential decay. Right? So there are variables that we had defined in the past. Okay. So what we did to solve these problems before is we used decimals. So like all those other problems that I showed you earlier, if you wanted to use decimals, graph the left-hand side, graph the right-hand side, that's fine. You can do that if you wanted. And I guess that would be one way to get around not using logarithms. But I'm showing you how to solve this using logarithms because it's good to learn things without the aid of graphing. Yeah. So anyway, so now with our new knowledge of logarithms, we can revisit all these problems that we went over in the past. Okay. So what I'm going to do is, in class, I'm probably going to ask you which method you prefer, and then I'll just go from there. And then I'll just choose the other one for the next examples or so, because there's 2 different approaches you can go for each of these. But anyway, so let's go ahead and just go through this. Okay, so what we said in this particular problem, so we have a certain stock, opens with a price of 59 cents. Over the first couple days, the value of the stock increases on average by 50% per day. And if this trend continues, how many days will it take for the stock to be worth $6? Okay, so again, keyword here is the stock is increasing, right? So stock is increasing, so that's going to represent exponential growth. So we're going to use that one. Okay, so all these variables here, this is all what we defined before, and then we can get to this point. Okay, so remember what I showed you in the past. To get around this, to actually solve it, we could graph the left-hand side. So left-hand side would be like y equals 6, and the right-hand side is going to be 0.59 times 1.5 raised to the power of t. So y equals 0.59 times 1.5 raised to the power of t. Okay, so this says, if we do it correctly, this says that it's going to take about 5.72 days. If you guys remember from that example in class, 5.72 days for the stock to reach $6. Okay. Now, with our new knowledge of logarithms, we can do this without actually having to graph it. Isn't that so awesome? So let's go ahead and do that. So we have 6 equals 0.59 times 1.5 raised to the power of t. Okay, we have this coefficient outside here, so I'm going to divide this by 0.59. Okay, so if I do this, I'm just using my calculator. I finally got my phone. It's next to me. Okay, so this here, if we cancel, this is going to be 10.169 equals 1.5 raised to the power of t. Okay, so now what we can do with this is we can go ahead and use our what we used earlier, right? So this is basically, we flip this around. This is 1.5 raised to t equals 10.169. And I can see some of you already, like Mr. Chang, get on with it. It's like, I know which one's a base, which one's an exponent, which one's the answer. Like, all right, fine. So do it however you want to do it, right? So our base, right? So our base is 1.5. Our exponent, our exponent is t, and then our answer is 10.169. So if our goal is to spell bay, so we have log bay, so 1.5, answer is 10.169, and we have our exponent, which is t. So if we go ahead and calculate this, log of 10.169 divided by log of 1.5. So if we actually do this, we can actually use decimals again. So we have, yeah. So either way, we're going to use decimals, or you can use some sort of calculator or graphing, or app to go ahead and calculate it. And log of 1.5. And that's 5.72. And look at that. We graphed it earlier. We got 5.72. And we did this and we got 5.72. Isn't that cool? Math is power. That's awesome. So this is t. So t is approximately, so we said earlier, so based on our calculation, this is 5.72. And then this is days. Okay? So that revisits what we went over previously. Okay, so that's one way that you can do it. Okay, so next, the method that I'm going to show you is I'm going to show you the method of using common logarithms instead. Okay, so if I use the method of common logarithms instead, so again, it's the same example that we went over before. So we have Sue has a lamp from her great grandmother. She has it appraised and finds it is worth $1,000. Okay, so originally it's worth $1,000. She wants to sell it, but the appraiser tells that the value is appreciating, so it's increasing by 8% per year. So that's going to represent exponential growth. How many years will the value of the lamp be worth 2,000? So we just plug in our values. Go ahead, do that. And then now when we get to this step, so now our goal is we want to sell for t, right? So if we want to sell for t, so a couple ways that you can do it. You could use decimals, or if you want, or if you wanted to, we can use our new knowledge of logarithms. So if we want to use our new knowledge of logarithms, so now what we're going to do with this is we're going to take this, we're going to divide by 1,000. Okay. So divide by 1,000, so we get 2 equals 1.08 raised to the power of t. Okay. So now what we want to do in order to try solve this, so the method that I showed you besides that other way, we could take the common logarithm. So we can, in this case, we have log of 2 equals, and then we have log of 1.08 raised to the power of t. Now, what we can do with this is we can take this exponent and drop it down. Okay, log of 2 equals t times log of 1.08. Now, we want to get t by itself. So to get t by itself, we're going to divide by log 1.08. Divided by log 1.08. So this is t is approximately, so let's go ahead and do that. So we have log 2. So log 2 divided by log of 1.08. Okay, so that's going to be 9.006. So 9.006. So that's approximately 9 years. It would take about 9 years for the value of the lamp to be worth 2,000. Yeah. So, like I showed you before in the past when we did a similar problem, what we did was we took y equals 2,000 on the left-hand side. Then we graphed the other side, so y equals 1,000 multiplied by 1.08, and we raise that to the power of t. And if we find an intersection point, it should be about 9. Let's hope it is 9. If it's not, we did something wrong. Oh, yeah, look at that. Oh, we good. 9.006. Yep. So, that's approximately 9 years. Okay? So, now, you see, the power of math. We can actually solve this without actually having to graph it. Okay, I'm going to show you 2 more problems, and that's it. Okay, I'll see you later. Bye. All right, let's go over these last 2 problems. Okay, so let's say we have the value of a truck purchased new for $28,000. It decreases by 9.5% each year. Okay, and we want to figure out after how many years will the value of the truck be worth $5,000. So again, take your variables, go ahead, plug plug it in, that kind of thing. And let's say our goal is to solve for t. Okay, so to solve for t, we want to get rid of this coefficient on the outside. So we're going to divide both sides by 28,000. Okay, so 28,000. So this cancels. And if we actually do this on a phone, so actually calculate this already. So this is going to be 0.17857 equals 0.905 raised to the power of t. Okay, so like I showed you guys earlier, so if you guys like the Bay method, I'm just going to flip this around. If you like the Bay method, this is basically 0.905 raised to the power of t equals 0.17857. Okay, so this is our base, this is our exponent, and this is our answer. So if we want to spell Bay, so we have log of 0.905. Our answer is 0.17857, and then our exponent is t. Right? So now what we want to do is we want to go ahead and solve for t. So if we solve for t, we use a change of base formula, log of 0.17857, and divide this by log of 0.905. Okay, so if we go to Desmos and actually calculate this, log of 0.17857 and divide this by log of 0.905. Okay, so it's going to be 17.259 or something. 17.259. T is approximately 17.259. In this case, this is going to be years. Okay, so if we round it to the nearest thousand. Okay, so another way that you could do it, you could also check your work with how we did this previously. So, graph the left-hand side, graph the right-hand side, right? So we have y equals 5,000, and then the left-hand side is 28,000, and then we have 0.905, and we're raising that to the power of t. Okay, and let's go ahead and look at that. 17.259. Yeah, look at that. See, we used logarithms. We didn't have to graph it. So, yeah, just wanted to show you that. Okay, so that's if you guys like the Bay method. So if you guys like the Bay method, this is B, this is A, and this is E. That's fine. You can do it that way. Okay, so last one, number 9, I'm going to show you that other way. Okay, so number 9 here. Okay, so on federal income tax returns, self-employed people can depreciate. Okay, so depreciate the value of business equipment. So we started with a computer valued at $2,765. Depreciates at a rate of 30% per year. And our goal is we want to determine the number of years it takes for the computer's value to be worth $350. Okay, so our goal, again, is we want to get t by itself. Our goal is to solve for t. Okay, so what I see is we're going to divide both sides by 2,765. So divide by 2,765. So this cancels. Left-hand side, we have to actually calculate it. So what we're going to get is we get 350, and we divide that by 2,765. So I'm just going to write this here. This is 0.126. I'll just keep a whole bunch of places, decimal places. 58, and this equals 0.7 raised to the power of t. Okay. So now what we're going to do is basically what I showed you earlier. If you guys like that method with common logarithms, so we can rewrite both sides with a common logarithm. So log of 0.12658 equals log of 0.7 raised to the power of t. Okay, so now what we're going to do is we're going to take this exponent here and we drop it down. So log of 0.12658 equals t times log of 0.7. Okay, so now what we're going to do is we need to get this t by itself. So if we get t by itself, we're going to divide by log of 0.7. Okay, so this cancels here, and our goal is to solve for t. So t is approximately, in this case, so we have log of 0.12658, log of 0.12658, and we're going to divide that by log of 0.7. Log of 0.7. So it's going to be 5.795, I guess. So t is 5.795. In this case, that's going to be years. Okay, so that's how long it would take. Looks like. Okay. Now, again, if you wanted to, you could go ahead and graph the left-hand side and the right-hand side, right? So if you graph y equals, so what was it, 350. So 350. And then the other side, we can graph 2,765. So 2,765. And then it was, 0.7 raised to power t. There we go. Okay, so change it up and look for our intersection point, 5.795. And would you look at that? That's exactly what we got there. So, all matter of preference, whatever you decide to do. Okay, and that's basically it for this video. Okay, so please let me know if you have any questions, and I'll see you later. Okay.